Hi everyone. Today I will going to explain you comparative study of d-orbital splitting pattern in different metal complexes. So before this we have all discussed the d-orbital splitting pattern in octahedral, tetrahedral, distorted octahedral complexes, in square planar complex, in trigonal complex, in linear complex. Such all we have discussed now. That put together I will going to explain in one picture, right? All the splitting patterns in one picture I will explain you. So this could be help you in understanding in comparatively from one splitting pattern to other splitting pattern, the differences and the splitting pattern change can be understood very well. I think so far I am giving you this video. So starting with the octahedral complex. Yeah, we are explaining all the splitting pattern in d orbitals. There are five non-degenerated there, right? 5 degenerated. So this 5 degenerated, when undergoing octahedral splitting pattern, we know that it derived two energy states such as Eg and T2G, right? The two orbitals get excites, reaches to higher energy, and those orbitals are dx square minus y square and dz square, get excites and reaches to higher energy. This is zero energy state, right? So thus higher energy state, these two orbitals get excites, and the three non-axial orbitals such as dxy, dyz, dzx get lowers their energy and has the T2G energy state, and excited orbitals will generate Eg energy state, and this excitation will has the reaching energy of plus 0.6 delta naught, and this also can be expressed in 6 dq, and lowering energy of non-axial orbitals will reaches minus 0.4 delta naught energy. It could also express in minus 4 dq, right? This is all in octahedral complex. 6 coordinated octahedral complex will has this type of splitting pattern, right? You know this, right? You already know this, right? And the da orbitals, when they participate in tetrahedral splitting pattern, the all 5 d orbitals, how they can split, it means we know that it is all slight reverse to the octahedral, right? The two orbitals of dx square minus y square and dz square get lowers their energy. The axial orbital get lowers their energy, and the non-axial orbitals dxy, dyz, dzx get excites their energy, reaches to higher energy, and this excited energy level represented with T2, the lower energy represented with E, and this is zero state, and lowering energy will be minus 0.6 delta T, and excitation takes place plus 0.4 delta T energy, right? Here the tetrahedral complex is 4 coordinated complex like this, tetrahedral and octahedral. This is known for you, right? All this known, but comparatively here we have taken the tetrahedral and octahedral. Then extending this, right, this comparison already I I given an explanation. Here I am extending for all the splitting pattern, right? Now I am going to have distorted octahedral, where there will be 4 energy state. The excited EG get splits into 2. The highest most excited energy will be has the orbital of dx square minus y square, and next energy state will be dz square. And the lower energy also gets splits into 2. T2g also gets splits into 2. That is singly state and doubly degenerate state, where dxy will get be slightly excited, dyz, dzx get further decrease in energy, and this excitation will has half of delta 1, half of delta 1 minus plus, and here plus 2.3 delta 2 minus 1.3 delta 2. Energy differences will be takes place in the next two energy levels of distorted octahedral. And the distorted octahedral structure, you know, the axial, the Z oriented bonds will be elongated. It is Z out structure, we know that, where metal to ligand bonds in Z orientation will be slightly elongated. This is distorted octahedral, right? Distorted octahedral splitting pattern, right? So by next I will going to express the square planar complex, and here square planar complex also has 4 energy states, right? I here didn't given the nomenclature of the uh, generated energy level in distorted octahedral. This highest most energy level can be represented with B1G, and next energy level represented with A1G. The dxy orbital energy level will be represented with B2G, and lowest energy level will be represented with EG, right? And next, square planar complex also has the 4 energy states, newly generated energy state in splitting pattern, right? And where dx square minus y square will reaches to the highest most energy level, and the next lowest energy will be dxy. The lower energy states are 2. One is single energy state, there is doubly energy state. The single energy state will be generated by dz square orbital. The doubly degenerate energy states will be generated by dyz and dzx, where the energy states are this. The energy states represented with here B1G, and it has the energy of minus 12.28 dq, minus 12.28 dq. The next energy state of dxy can represented with B1G, and it has the energy of, sorry, it is plus, na? Plus only, right? 2.28 dq, 2.28 dq. The lower energy states of dz square orbital can be represented with A1G, and its energy is minus 4.28 dq. The lowest energy state Eg has the energy of minus 5.14 dq. Minus 5.14 dq. It is for the square planar complex. Right. 4 coordinated square planar complex. And we have two left, two more, that is trigonal and linear. Coming to trigonal, trigonal energy state will be, has three energy states. One is the singly degenerated doubly degenerated state, which has the dx square minus y square and dxy. Then the other two are in another two in lower energy state, where one will be lower energy singly state and the other will be doubly degenerated state, right? And the singly degenerated state has the orbital of dz square orbital, and the doubly degenerated state has dzx and dzx and yz, right? That's how the orbitals and their energy states can be represented with, here it is represented with E bar. The doubly degenerate state in higher energy state will be represented with E bar, and it has the energy of 6.28 dq. The lower energy state of singly degenerate state dz square orbital energy state has minus 3.21 dq in energy, and the doubly degenerate state represented with E double bar. Sorry, it is B1, sorry, A1 only. The dz square orbital represented with A1, and the doubly degenerated state will be represented with E double bar, and it has the energy of minus 3.86 dq. 86 dq, right? And the final one, the linear, has the energy state, three energy states. One is highest most, and it has the orbital of dz square, and the left next higher energy state will be doubly degenerated state, has the orbitals of dyz and dzx, and the lowest energy state has another doubly degenerate state. It has the orbitals of dx square minus y square and dxy, and the energy state representation, the dz square orbital represented with a1g, and its energy is 10.28 dq. The second highest energy level, right, has the energy of 1.14 dq, and represented with E double bar, and the lowest energy state represented with E bar, and its energy is minus 6.28 dq. This is what for the linear. Trigonal complex, and this is linear complex. Right. So this is how the splitting pattern in all major types of complexes, structural complexes such as octahedral, tetrahedral, square planar, trigonal, linear, and their splitting patterns of valency d orbital. Right. Here in comparative, what we can say that the d orbital, right, when it is go under in splitting pattern, right, if the structure is octahedral, it has two energy states such as T2g and Eg, where T2g axial orbitals will generate the T2g orbital, T2g energy state. The axial orbitals of non-axial orbitals, the non-axial orbitals of dxy, dyz, dzx, which are away from the ligand sites, right. Here in octahedral, we know that the ligands approaching along the coordination axis. Along the x-axis there are two orbitals, along the y-axis there are two ligands, along the z axis there are two. On each coordination axis there will be two ligands approaching towards the metal. So as the ligands approaching axially, the non-axial orbitals of dxy, yz, zx, these three can lower their energy. Having no interaction with ligand sites lowers their energy, reaches to T2g energy state, reaches to 4dq, minus 4dq in energy, has the energy state, represented energy states will be T2g. The axial orbitals such as dx square minus y square and dz square, right, having interacted with the ligand site, all six ligand sites can approach these two ligands, will have repulsive interaction with these two orbitals. So having these orbitals, axial orbitals of dx square minus y square, dz square, get distorted, get destabilizes their energy and excites their energy to reach plus 0.6 delta naught or 6 dq in energy as the newly energy state, generated energy state, represented with Eg. Same scenario when it come in tetrahedral. In tetrahedral also there are two energy states can be generated, but here the generated new energy states are in energetically they are totally different from the octahedral, but their orbitals, with respect to of orbitals, newly generated energy levels are similar to the octahedral, and the splitting pattern is in tetrahedral is quite exactly reverse to the octahedral splitting pattern. The axial orbitals such as dx square minus y square, dz square get their lower energy state, lowers their energy as they are having not having any interaction with ligand sites. They can lower their energy and reaches to minus 0.6 delta naught energy, whereas the non-axial orbitals of dxy, dyz, dzx get slightly sidewise interactions in tetrahedral complexes, get slight excitations and generates a new energy state of T2, right. Such tetrahedral, octahedral splitting patterns will be there. When it comes to distorted octahedral, this distorted octahedral splitting pattern is also called as John-Teller distortion. The John and Teller express their theory in distorted octahedral splitting pattern to defining the distorted octahedral splitting pattern. The John and Teller gets their theory and thus gives you distorted octahedral splitting pattern, where the octahedral, newly generated octahedral splitting pattern, Eg, T2g energy states never be stable, right. These two energy states in octahedral such complexes never be stable, they undergo in further distortion, right. The John Teller describes the theory as the non-linear complexes with asymmetrical uh, electronic configuration, valence electronic configuration, will undergo further splitting pattern, right. So octahedral such complex, which is non-linear complex, when having asymmetrical electronic configuration, which means that unequal electronic distribution in newly generated energy stable, right? T2G, EG, when they are having unequal electronic distribution, these T2G and EG will be never be stable. The energy states of T2G and EG will be never be stable. They undergoing further splitting pattern and generates the distorted octahedral splitting pattern. That is what the John Taylor expressed. And in this, the EG state, when having asymmetric electronic configuration, gets splits into two energy states, that was B1G and A1G. In B1G, the EG energy orbital having dx square minus y square get excites, reaches to higher energy level, generates B1G energy state, and the dz square orbital slightly lower its energy and generates the A1G energy state. Similar to that, the T2G also, when it having asymmetrical electron configuration, gets splits into two energy states. That's how the dxy orbital slightly excites and reaches to higher energy in comparative of this T2G energy state, and the left two dyz zx orbital gets slightly lower their energy and reaches to lowest energy state of EG, right? Such how the distorted octahedral splitting pattern can be expressed, or John Taylor distortion can be expressed, right? This splitting pattern, when extended to the square planar complexes, square planar complex is four coordinate complex, where this four coordinate complex having splitting pattern, ligand interaction with metal valency d orbital, has four newly energy states, right? Where the dx square minus y square orbital having all four ligands oriented towards the dx square minus y square orbital get interacted with all four ligands with this particular orbital, so have highest most interaction, highest most destabilization, repulsive interaction, destabilization, so excites in an higher energy state, highest energy states, that of 12.28 dq, right? And it generates an B1G energy state. There next, the dxy orbital also having partial sidewise interactions with the all four ligands in square planar complexes get slight excitation, and that reaches to 2.28 energy state, generates B1G energy state, sorry, B2G energy state, B2G energy state. Then it follows the other three orbitals, where the dx square minus y square get lower its energy since it has no interaction with ligand sites, reaches to lower energy state, that is minus 4.28 dq energy state, and it has the representation of A1G. The left two dyz and dzx orbital will reaches to lowest energy state, represented with Eg, that is minus 5.14 dq in energy, right? This is how the splitting pattern in square planar complexes. When it comes to trigonal complex will have three newly generated energy states, where the dx square minus y square and dx square minus y square and dxy orbital get participated in interaction with ligand sites. Thus interaction will destabilizes the orbital and reaches to higher energy state, that is E1 bar, and it has the energy of 6.28 in dq, and the left three orbitals will be get lowers their energy, where the dx square minus y square will reaches to lower energy state of a bar, and its energy is minus 3.21 dq. The left two dxy dyz orbitals reaches to lowest energy state, and that is minus 3.28 dq in energy, and it represented with E double bar. This is how the splitting pattern in trigonal complex. Now coming to the last but not the least, linear complex splitting pattern. The 5 d orbitals get splits into three energy states, where the z oriented dz square orbital has highest most interaction. All the two ligands will interacted with dz square orbital, This interaction will makes the dz square orbital to destabilize in more extent and reaches to higher energy state, that is what 10.28 in dq, and it is represented with a1g. Then next, orbitals of dxy dyz have slight interaction, very partial interaction will also makes the orbitals to reach slight excitation, and it is 1.14 dq in energy, represented with E double bar. The left two orbitals of dx square minus y square and xy get lower their energy because of no interaction with all the two linear ligands, so reaches to lowest energy state, that is what E bar, and its energy is minus 6.28 dq, right? So that's how the all splitting patterns, all 6 types of splitting patterns in metal complexes and their comparative statement here we can record like this. So here I stop. Hope this video will help you in understanding splitting patterns in different major types of metal complexes, and that's how the video. Here I stop. Thank you.